Welcome back. So let's continue on forwarding. So if you remember last time, we talked about this problem of what we call data hazards, right? And I kind of break it down into various different types of hazards. And then within the data hazards, we also talked about different types, including read after write, which we call raw data hazard. And then there was write after write and write after read and read after read. Read after read one was of course not a hazard at all. Write after read and write after write, we said that essentially as long as your system is in order, that you guarantee that instructions are going to be executed in order, then we are good and there's nothing to be worried about. It's a problem that we're gonna later kind of revisit and talk about when we are talking about out of order processors. So the only thing that we need to kind of be worried about was this read after write thing. The reason that we had this problem was that in a pipeline processor, we start overlapping things. So there will be two cycles where the previous instruction hasn't been finished and the write to the register file hasn't been updated. And if you try to read the destination register during that 2-cycle window, you're going to get into the problem of raw data hazards, right? And we started talking about, okay, how do we fix this? First of all, we saw that in our pipelines, 5-stage pipeline, there's only 2 cycles that we need to be worried about. I kind of briefly talk about other kind of designs, and we said that necessarily not 2 is always the answer. But for our design in this course, it's always 2, okay? So what should we do? I said that the easiest thing that we can do is stalling the processor. The stalling was this process of not letting some instructions go inside the pipeline. And instead what we're doing is we kind of like don't let the particular instruction to go forward. Instead, we're kind of injecting what we call a bubble. And we need 2 bubbles in order to kind of fix the issue that we have, right? So that was kind of the idea here, that we kind of like add 2 new slots in our execution. We insert this bubble and then we let this sub go at this point. So we call this a bubble. I said that this bubble thing is not the best solution because essentially we are reducing our CPI from 4 to kind of 2 for these particular type of instructions, right? And the bubble, as I said, is this kind of special instruction. It's not like really an instruction. It's kind of something that we do in the hardware. So it's not really going to the fetch, decode, execute, memory, and write back. We kind of substitute the sub with the bubble during the execution, memory, and write back. So it's kind of like if this is your 5-stage pipeline, so you had add here, for example, and you had sub here, and maybe the next instruction here, I3 or whatever you want to call it. At this point, since the sub is kind of dependent on the add, the next cycle we cannot do add. So let me kind of write it. Actually, let me do it this way. So if you had something like, so this is fetch, decode, execute, memory, and write back. So if in this cycle, I have sub here and I have add here. If I go to the next cycle, then I usually do sub and add, right? But since the sub cannot really go forward, what we do instead is that we inserting kind of the bubble at this point. So we will have the bubble, add, and something else. So before and after, we don't care. And then since we need to have another cycle so that this add reaches to the write back stage, we're going to have so sub stays in the decode stage. we will need to insert another bubble since the sub is not really moving forward. This bubble goes into the next cycle, right? And then now this adds goes into the write back stage. And now we can actually, in this cycle, we can let that sub go. So in the next cycle, what we will see is the sub now goes to the execution stage, right? And then the rest of the story. So it's kind of like, we're stalling the processor for 2 cycles. Instead of moving the sub into the pipeline to the later stage of the pipeline, we're substituting with these 2 bubbles, okay? So this is kind of like that's description. And then we came with this idea that, okay, is there any other solution that could do better than just inserting bubbles? In other words, if I want to really prevent the stalls from happening, is there anything that I can do? And then that comes the idea of forwarding, okay? So the idea of forwarding is basically we are bypassing this idea of, oh, I need to write to the register file and read from the register file. I still need this for the future instructions, but for that 2 cycle window that I haven't updated my register file yet, maybe I can kind of rewire things because I already have the data. So I can rewire things such that, I can temporarily, access that particular value, okay? So how do we do that? We kind of said that since these are 2 cycles, I need to kind of have 2 types of forwarding, right? The first forwarding I need to do is that if there is one instruction and the next instruction immediately after, so this 1 cycle, just, exactly after one after another, I need to forward from the outcome of the ALU, or in other words, the input of my memory to the beginning of my ALU. Because basically what is happening here is that this sub instruction is reading the register file, but since the register file hasn't been updated, I kind of not reading the correct value here, right? So whatever value I read here, I need to kind of replace that value with the correct value that's being forwarded by the previous instruction. So I kind of like literally kind of have a wire that's connected from the outcome of the ALU to the input of the ALU. Then there is also the second instruction that might be, dependent. So not these 2, there might be also these 2 instructions dependent to each other. In that case, forwarding from ALU, outcome of the ALU to the input of ALU would not be enough. Why? Because now add is actually in this memory stage. It's no longer in the ALU stage. So I also need to forward from the memory stage back into, again, the beginning of the ALU stage. Okay, so forwarding happens either at the output of the ALU to the input of the ALU, or from the memory stage back into the ALU. So the kind of the place that we forward to is the same. The place that you're forwarding from, depending on which cycle we want to forward, could be the different. Okay. So we usually do this for of course for the registers, right? So from ALU results to ALU source, and from memory to ALU source. These are the 2 things that we're going to do, okay? So before actually showing you how do we do this, I also want to point out that there's also this question of, is this going to fix all of our problems? Is it guaranteed that if you forward from ALU from the output of ALU to back to the ALU, or from the memory to the ALU, is it everything that we want? And the answer to that is unfortunately no, because of the load instructions. So how does the load instruction works? So if you think about the load instruction and the data that comes from the load. So for example, let's say we have an instruction like this, that we have load word x5, 40, and x2. So what does this do? It's kind of look into the content of x2, add that with 40, and that's the address of the memory that we're going to access. And whatever content that is stored there, you're going to load it into x5, right? So x5 is the destination register. So if I have another instruction immediately after that use x5 as the source, we're going to have the same issue of data hazards, right? So this is different than the ones that I showed you before, because that one was like an R-type instruction or I-type instruction, but this is a load instruction, okay? So what is the difference? The difference here is I don't have the data at this point, right? I have the data at this point, at the outcome of the memory, because I need to go to the memory, bring that data, and that's when I'm going to have the correct value for X5, okay? So when is this available? At the end of the cycle. Remember, reading from memory happens in the second half of the cycle. In other words, I don't have this result until the very end of this clock cycle, okay? So if I want to do the ALU operation in the same cycle, I cannot do it because the ALU operation happens somewhere in between, but this value is only available at the end, okay? So in other words, if I want to forward from here to here, the timing wouldn't work because that data is only valid at the end of the cycle, but I need it during the cycle. So there will be a kind of a race condition issue. So in that case, forwarding from end of memory back to the register to the ALU won't work. Okay, so we are kind of going back to this problem of I need to stall. The good thing about this is that I not only need to stall for one cycle, because if this thing goes into the next stage, then I can forward from here back into here and I'm good, right? So so I only need to kind of forward for one cycle, stall for one cycle instead of two, because in the next cycle I can use forward. Okay, so the difference between what we call a load use data hazard versus a register data hazard is that in registers I can do forwarding. Why? Because I have the data available at this point, because this is basically the results of adding or doing some arithmetic operation to my register files, to my registers here and here. But for the memory operation specifically, since this value, this correct value, is only available at the end of the cycle, I cannot really use that during that cycle. Okay, so that's kind of the difference between the two types of hazards. All right. But what are we doing? So for load use hazards, we're going to kind of do the stalling, inserting bubble. But as I said, you can use forwarding from here to here, and that will fix the issue of not stalling for two cycles. So if they didn't have the forwarding, then we had to kind of stall for two cycles, back to the issue that we have. So we stall only for one cycle, and then we do the forwarding from the input of the register file back into the ALU source, okay? So kind of the combination of two things. In register type, data hazard, we do forwarding. We don't need to do any sort of stalling. For load use data hazards, I need to do forwarding, and I still need to do the forwarding and the stall, okay? So the question question.
So looking at the let's we still go with everything and we do it all. Just like there's no like everything there.
What do you mean by everything?
Like all of those registers, all that.
So the question is, for a no-op, do we go through all the stages or not? As you can see, what is happening here is, so if I go back to that examples that I gave you, so what is happening is that this is kind of like the current situation in your pipeline, okay? You have your sub in the decode stage and you have your add in the execution stage, okay? And there won't be some other instructions, I don't know, like an X or whatever, the next instruction in the fetch, okay? Now you realize that, oh, I have a problem with the sub. I need to stall my processor, or I need to insert a bubble. So what I would do is that I'm going to, since in normal world, this would have moved to this stage, right? So this would have moved here, this would have moved here, and so on and so forth. Since I cannot really move the sub to the next stage, I'm replacing the sub with the bubble. So the bubble really doesn't go through the fetch or decode. It's just replacing the sub during the execution, memory, and write back stage, okay? And if I need to keep inserting bubble, I keep inserting it during the execution stage. So the bubble really is just a special instruction that's replace my previous instruction during execute, memory, and write back. Doesn't really go to the fetch and decode. Does that make sense? Any other questions? Okay. So going back to this question of, okay, now we know that we have this problem. We either need to do the forwarding or we need to stall at least one cycle and then do the forwarding, either of these two. But the question is, how do we even detect that we need to do forwarding or we need to do stalling? As I said before, we're going to have this, what we call a hazard detection unit, okay? And what this hazard detection unit is going to do is this very simple check, okay? So for my raw data hazards for registers, this is what we are going to check, okay? So if we're going to see that there is the RD of, let me use a different color. So if I see that the RD of execution memory stage is equal to RS of IDEX stage, so the RD of my execution or my memory stage is equal to one of the RSs, one of RS1 or RS2, and if I see that, this is actually an R type or I type instruction, in other words, the reg write is equal to 1 for that particular instruction, then I understand that I need to forward from the EXM mem register to the beginning of my ALU, okay? And similarly, if I see that, my mem write back is similar to RS1 or mem write back RD is equal to RS2, either of these two. And again, if this is an R type or an I type instruction, I see that now I need to forward from memory write back stage back into the ALU. So basically, this is similar to what I'm showing here, okay? So going back here, so either I forward from this register, okay? So either I forward from this register or I forward from this register. If this is these two instructions, so if the IDEX RS1 or RS2, which means that either this kind of register here or this register is equal to RD of EXM mem, which is the instruction that is here, which means that this instruction and this instruction are kind of dependent to each other. So I need to kind of do the forwarding. Or if I see that basically the RD of this register is similar to RS1 or RS2 of this instruction, then I need to forward from this register back into the ALU, okay? So basically either of these two, either there is the dependency between the add instruction and next sub, or there is a dependency between add instruction and the second instruction, okay? So either of these two, right? So this is, and then the reason that I'm checking that whether reg write is equal to 1 or not is because I only want to forward if this is either an I type or R type instruction. Otherwise, there's no point of doing the forwarding because RD in that particular instruction is not even used. Okay, so there's no need to forward. Okay, so this is kind of the reasons that we are doing either of these two. And then one thing to look at is X0. So there might be a scenario where RS1 is X0 and RD might be also X0. So in that case, you really don't need to do the forwarding, right? Because in either case, it's always 0. But if you also do the forwarding, nothing bad really happens either, okay? But we typically don't do forwarding if both of them are X0, okay? So this is the data path with this additional changes. I kind of showed this before, but let me do it one more time. So as you can see, we either forward from this register or we forward from this register, okay? So the way this works is we're going to get this value all the way from here, okay? Or we're gonna get this value all the way from here, okay? So this is the beginning of this register and this is the beginning of this register, all right? And then the same story goes for, this is for RS1, this is for RS2, okay? So we either need to forward from RS1 or RS2, and as you can see, we are adding this additional multiplexer that gets this control signal forward A or forward B, okay? And this forward A or forward B is the ones that is detected by this, what we call a hazard detection unit. So basically, the moment that we see that the RD of a future instruction is similar to either RS1 or RS2, we're going to issue the forwarding so that we can basically, instead of selecting the regular RS1, we either select this RS or this RS, depending on which stage we need to do the forwarding from. Okay, so that's kind of the idea. And this is the kind of forwarding or hazard detection unit that we're going to have. So it basically, as you can see, it takes RS1 and RS2 as the inputs. It also takes the RD of these two registers from here and here as the inputs, and it issues this control signals, okay? So this control signal is usually different than your regular control signals. It's kind of a separate unit that we usually put at somewhere else in our design, okay? Any questions about this? Any doubts? Yeah.
Can we go through an example of how the signals would work and how the selection happens to the works to the forward?
Say the first part again. How does what work?
Go through an example of how the control would work.
Yeah. So for example, let me see if I have anything here. Okay, no. So essentially what will happen here is so let's say, for example, I have add X5, X4, and X3, and then I have a sub X6, X5, and maybe X1, okay? So I have something like this, right? So what will happen is that if I have my fetch, decode, execution, memory, write back, so this add goes here and then goes here and then goes here. So this would be my add, for example, after the third cycle, and this would be my sub, okay? So at this point, here's what we're going to check, right? So we're going to check and see that the RD of this instruction, so if I show you here, you will see that the RD of this instruction that is currently here will be similar to the RS, one of the RS of this instruction, okay? In that case, what we are going to do is that we are going to issue the forwarding in the next cycle, which means that this RS would have been the normal RS, but instead we're gonna, for example, say that forward A is now should equal to 1 or 2, which means that this basically, this number that we're gonna select here, the number that we're going to select here is now coming from this value instead of this value, okay? And what is this value? This value is coming from all the way from here, okay? From the next stage of my pipeline. So going back again here, next time that in the next stage, what I'm going to do is that I'm going to pass the sub to the execution stage and I'm going to pass the add to the memory stage. The sub reads an incorrect RS. So what I'm really doing is that I'm forwarding this value back to the sub, right? So the sub is now in the execution stage, the add is in the memory stage. I'm forwarding the value of RD from the memory stage back into my execution stage, okay? This is kind of like what you're seeing here, that this value is really coming from where it's coming from this point here, from here, okay? This is the RD that's coming. And the same story goes for if I have a scenario where I had something like this. If I had add X5, X4, X3, maybe I had an XOR in between that is like X6, X0, and maybe X1. So there is no dependency between these two, but then I have the same sub here, okay? So let me actually change this to X7. And then I'm going to have the same sub, X5, X6, X5, and X1, okay? Now there is a dependency between this instruction and this instruction, okay? So in this case, if you go back to this kind of design here, what we will see is that if this is fetch, decode, execute, memory, write back, my add is here, my XOR is here, my sub is here, right? And since XOR is not dependent to add, I can just move things forward. So XOR goes here, add goes here, and then the sub goes here, right? And this again, where we're gonna check this the condition, but this is the second condition. This is the condition between the RS RD of mem with the RS of sub, and see, okay, now I see a connection. So what will happen is that in the next cycle, I'll let the sub goes here, XOR goes here, and right back add goes to the right back. And now I forward from here to here, okay? So again, going back to this design, you will see that basically I'm forwarding from here back to the here. So this is the second line. So there are two things that goes into this 3 mux. The regular value of RS1, the forwarded value that comes from this stage, and the forwarded value that comes from this stage. And this forwarding unit will tell us which one to pick. In regular case, I'm going to pick this one if there is no forwarding. If the forwarding needs to happen from this stage to this stage, I'm going to select the second one. And if the forwarding needs to happen from this stage to this stage, I'm going to select this one. And this is the mirror between RS1 and RS. So whatever I do for RS1, I'm going to do the exact same thing for RS. Okay, that's kind of the idea.
Okay, so just a clarification, the red line, is that supposed to match up with the red line in the box? Because I think it might be a different line.
Which red line? I have many red lines.
Sorry, the one coming out of the EX/mem.
This one?
Yeah. So that's supposed to connect with the red line in the middle of the box, right?
Yes. So if I follow it, you see that it's kind of coming down here. Let me see. Yeah, it's kind of coming down here, goes here, and goes back up here. See, so this is the one, right?
Wait, but it's not connected to the bottom part?
No, this is like this. So usually what we are doing here, like you see that, for example, there is an overlap here. The notation is that if there is a dot, they are connected. If there is no dot, then they're not connected.
Okay.
Does that make sense?
Yeah.
Okay. Any other questions? The question is, what if you need both? You can do both, right? Because you can issue both of them, because the forwarding unit checks this independently, right? So you can both issue forward B and forward A at the same time. These are two wires, right? You can just connect both of them. So if you need forwarding same value, or even you can have a very complex system where you are dependent from RS1 and RD from between the execution and the code, and there might be also RS2 is also dependent. So like both of them are kind of dependent. In that case, you kind of forward both of them, right? Because they're independent. Yeah.
So the hazard detection is automatically triggered with this forwarding unit.
Yes. So the question is, the hazard detection unit or the forwarding unit automatically decide that? Yes. As you can see, the hazard detection unit basically takes these two values and also takes these two values here and here, which are the RDs. Okay. So it takes the RDs, it takes the RSS, and then decides what we should do. And everything happens independently, which means that if I need to forward both, I do. If I need to forward one, I can, and anything else. Any other questions? Perfect. So what we do for the load use? For the load use, we are checking basically whether or not the IDEX and IFID or IDEX and IFID of the destination registers are the same. In this case, I need to stall for one cycle, and then I need to forward in the next cycle. Okay, and I'm gonna let you guys to think about why this is IDEX and not EXMEM. If you have questions, you can ask me on Campus Wire, but think about why in this case this is one stage before. To kind of give you a hint, probably you want to kind of put it into the like this fetch the code, execute memory, and write back stage, and then you will see where the timings is kind of basically coming from. Okay. But think about it, if you didn't understand it, you can ask it on campus, or I can show it to you. And then one last thing I want to show you is basically what we're going to have is that I'm going to have forwarding. Okay, so I'm going to use this terminology that I use what we call a hazard detection unit for stalling the processor, and I'm going to use a forwarding unit for doing the forwarding. So I'm going to distinguish these two from each other. As you can see, I'm going to have a hazard detection unit up here, and I'm going to have a forwarding unit up here, down here. What's the difference between them? The hazard detection unit is the one that decides that the processor needs to be stalled. Why do we need to stall the processor? Because of the load use data hazard, right? So we need to stall the processor for 1 cycle. And the forwarding unit helps you for doing the forwarding, okay? So how does this hazard detection unit basically works? It's actually, in order to kind of insert the bubble, we are using this very, very simple trick. So as you can see here, what is really happening is this hazard detection unit has this output that is basically a mux that kind of sits in between the controller and my pipeline registers. And what it does is basically replacing all of my control signals with zeros if the hazard detection unit decides that it needs to insert a bubble, okay? So basically, what is a bubble? Bubble is an instruction that all of its control signals are equal to 0. If you remember, I told you that we are designing active high, which means that if things are equal to 0, means nothing will happen. If things are equal to 1, it means something will happen. So essentially, in order to insert a bubble, all I need to do is that replacing the actual control signals with zeros, and then feed that into my pipeline register. So what will happen is now it's basically this all 0 kind of control signals will move forward. I don't need to change these other data values. I don't need to kind of go and replace everything with 0. All I need to do is basically just replacing my control signal with 0. And that's sufficient for making sure that nothing happens to my instruction, okay? So hazard detection unit, all it does is basically adding this mux on the path of the controller and replace your controller signal with all zeros if it needs to insert a bubble, okay? So that's basically what it does, all right? And another thing that you will see is basically we also need to stop the kind of the sub instruction to move forward. So we need to kind of literally stall the processor. So what it does is adding these 2 additional signals, this one and this one. And these are basically telling these 2 registers, the PC register and the IFID register, to not to move forward, okay? So this is basically, so this means that these 2 instructions, the instruction that is staying here and the instruction that is staying here, they will just keep staying in those pipeline stages. So basically, this is kind of like a write enable for this register and write enable for this register. I'm telling these 2 registers not to update, even if the positive edge of the clock comes. Why this is the case? Because this will means that this instruction and this instruction will not get updated. They stall until this processor decides that it no longer needs to stall the processor. For load use, it's just 1 cycle. So essentially, we're telling these 2 control signals to stop for 1 cycle and then move forward regularly, okay? So in other words, these 2 numbers are always 1 unless we want to stall the fetch and we want to stall the decode stages. If you want to stall those, then they become 0, which means that these 2 registers won't get updated. They still, they contain the same value that they have, okay? But the rest, they can just move forward regularly, right? So this is kind of the idea.
Yeah, is it kind of like a D flip-flop, or is it just too granular information? Like how you prevent it from like updating?
Yeah, so how do we prevent it from updating is basically, if you remember, a very long time ago, I told you that the register has a clock and has a data, but some of these register also has what we call a write enable, okay? So basically what this does is that it makes this write enable equal to 0. In that case, even if the clock comes and the data changes, this output won't change, right? So this is kind of like what we did. So it's a flip-flop with the write enable. Any other questions? Okay, so there's lots of things going on. I definitely recommend you to kind of take a look at all of these and see what are the changes that we are making. But essentially, the big changes that we are making is adding this forwarding unit here, and kind of adding these two new muxes. So this mux is in addition to the muxes that we had. We're not replacing anything, we're just adding things. So we have this mux and this mux, and then this forwarding and this forwarding. And then of course, there are kind of that new wiring that needs to be done. So this is one thing that we are doing. The second thing that we are doing is we are adding this hazard detection unit in order to stall the processor. And then what this does is basically, first of all, deciding whether we want to stall the processor or not. And the second thing it does is basically adding this multiplexer that's kind of replacing all the control signals that's coming from the controller with all zeros. So basically, this is kind of like what we do here. And in addition to that, since we need to literally stall the processor from progressing forward during the fetch and decode stage, we are adding these two additional control signal, one here and one here, which is basically telling the PC and instruction fetch / instruction decode pipeline register to not get updated. So whatever instruction that was here stays here, whatever instruction that was here stays here, everything else just moves forward. Okay, so this moves forward to this stage, this moves forward to this stage, and this instruction that was here is going to be finished. Okay, so execution, memory, and write back continues normally. Fetch and decode kind of freeze. Okay, and then we continue doing this until we realize that it's now time for the whole pipeline to go forward. Okay, yeah.
Explain again, like setting the control signal at the top of the
Why zeroing? What does zeroing does? So the question is why we are zeroing this thing. So if you remember back in when we were designing the controller, we said that, for example, reg write equal to 1, mem write equal to 1, and so on and so forth means that we are updating something, right? If everything was equal to 0, basically nothing will happen, nothing will get updated, right? So this is kind of like that idea. Since we are doing active high, which means that if it's 1, we're going to do something. If it's 0, we're not going to do something. Then in this case, we're just replacing everything with 0. In that case, we're not going to update our register file. We're not going to update our memory, and we're not going to update our PC. Neither of these three will happen, right? So in that case, we are good to go. This is kind of like a no-off operation. It still does something, it does some switching, but that switching is basically just garbage switching. Yeah, so I'm kind of like also emphasizing on these three. All right, so this is kind of it for my data hazards, okay? We're going to give you like a homework to play with it, to kind of like see what's the different cases for data hazard. Pay good attention to kind of these designs here, to kind of like, learn the differences. And then, by the way, as you've seen, the project is out, right? Your first project is out. The project will be about designing just a regular data path and controller. So now you're not going to implement this, just going to implement the regular data path and controller. Just go to the website, see the description. It's going to help you with with your quiz 1, because quiz 1 will be all about designing the data path and everything. But you won't have much time, okay? So start early. Hopefully you have already started. If you didn't, plan to start this weekend, okay? So if you remember, I told you that there are three types of hazard. There is data hazards, there are structural hazards, and there are control hazards. So far we talked about data hazards. Let's talk about the other two. So a structural hazard is when there is a unit that is busy. So for example, if you want to use a register file to read a value, but that register file is being used by another instruction. In our design, we're not going to have a structural hazard because we are designing our processor, our data path such that we have enough ports for example, memory, or enough ports for the register file to kind of do things simultaneously. If we had designed things different way, we might have structural hazard. So a structural hazard is basically an important issue, but in our design is basically never happens because we are designing our processor such that it never has a structural hazard. So that's one thing to remember. Again, for example, if I had something like this so remember our kind of register file is like this, right? So we have RS1, RS2, RD, and data for data writes, right? So I have 4 different kind of independent inputs. But for a moment, think about if I had designed this like this, that I had maybe RS1, like I only had 2 ports. So I could only either read RS1 or RS2, or I could read RS1, for example, and RD. In that case, there was a contention between instructions. Maybe one instruction wants to read, the other instruction wants to write. And in this case, we call it a structural hazard because I cannot do the same thing at the same time. So I need to kind of either stall the processor or do some other tricks. But as I said, in our design, since we are kind of designing everything to be able to do this in parallel, we're not going to have a structural hazard. So that's one thing to remember. But then there is also another question that we're going to step the rest of this lecture about, and that is what will happen with the branch instructions, and basically what we call control hazards. Okay, so and then this control hazards is actually an interesting question that we're going to see. So let's have a quick break, and then we'll come back and then talk about this branches and structural hazards. All right, so let's talk about what is happening with branches, okay? So what about branches and why branches is all of a sudden important things to think about is because if you think about the way that we write our codes, we write our code in kind of a linear fashion. Yeah. Oh, you missed the code part. Good. All right. So if you think about the way that we write codes, we kind of write codes in a linear fashion, okay? And if you think about kind of the CFG or the control flow graph of the program that you write, it looks kind of like this, that like you have like a code block A, you get into the condition, and this condition is either true or false, right? 2 outcomes. If it's true, then you write, you execute one code block, for example, in this case, kind of the condition inside the if is true, or you just run the false. So kind of like you run this, right? And then after a while, they both converge into some code block D, okay? So it's kind of like, you kind of go this way or this way, right? But if you think about the kind of the way that we put this into our data memory or instruction memory, memory is kind of a linear thing, right? So there is no kind of like 2 path that the way that we have here. So if this is our kind of code for A, we need to now decide whether we want to put like B after this or C after this. So let's say, for example, we put C after this. So this would be C, but regardless of whether I put C or B, if the condition is kind of true or false, then I need to kind of either skip this part or I need to skip this part, okay? So I need a mechanism to kind of jump over a particular part of the memory, right? So all this kind of ideas of, okay, I do PC+4, PC+4 works until we have something that we need to kind of decide to jump over, right? And we kind of fixed this problem with when we were discussing how do you update your PC by PC plus offset and branching and all those things, okay? But if you think about the pipelining is kind of works with this way that you kind of have a sequence of instruction and kind of like keep pushing things inside your pipeline, right? So as you're kind of fixing an issue for one instruction, like doing an execution for one instruction, there is another instruction that comes to the decode, there's another instruction that comes to the fetch, and so on and so forth, okay? And the problem that's going to happen is sometimes we don't know what instruction to fetch, because if we are getting to the situation like this, like at this point here, we don't know whether it's going to be C or going to be B, right? So we kind of like, we need to kind of resolve the branch first in order to decide whether we have to fetch the block C or block B, okay? But if you think about the pipeline, you will see that actually the time that we resolve the branch is not immediate. It takes some time for the branch to be resolved. So let's talk about that and see when this happens and see why this is going to be an issue. And again, you might ask why control hazard wasn't an issue in single cycle. And again, the answer to that was in single cycle, we finish one instruction and then start the next instruction. So by the time that finishes that instruction, we already knew that, for example, this branch is taken or not taken. So the next instruction is already known at that point, right? We already know that, okay, this is a taken branch. So I need to go and, for example, load from the C block. If it's not taken branch, I need to go and read from B block, and so on and so forth, okay? But for the pipeline, this is an issue that we're going to have, okay? So how do we, resolve the control hazards? Okay, what's the problem, and how should we resolve the control hazards? So the first question that's like, the first solution that's come to the mind is the same old stalling. Okay, that if the branch comes, stall the processor. First, figure out where the branch goes, whether it's taken or not taken. Once we know the kind of outcome, then we can kind of, fetch the correct instruction and continue, right? So that seems to be a good solution, but there are kind of two main questions of this. First of all, how many cycles do I need to stall? Like, when do I know the branch is, like, what is the location of the branch and whether the outcome of the branch? How do we do the stalling of this? How do we do the detection of this, and so on and so forth? And then the second question that we always ask is, are there better solutions? Okay, so let's talk about each one by one. Let's first talk about this stalling and say, okay, this is the best solution that we can do. And later on, we're going to talk about how to improve that, how to make this even better. Okay, so in order to kind of like find out the kind of why and how problem, you have to always go back and kind of answer these three main questions from a controlled flow hazard. We call it 3W questions. So basically, when the branch happens, where do we branch to, and whether to branch or not, okay? So when the branch happen means that when do we know that this is a branch instruction, okay? Because, different instructions come to the pipeline, not all of them are branched. So we need to first know when this is a branch. The second is, if this is a branch, what is the address that we are going to jump to, okay, if we know that this is a branch. And the third is, we don't know even we're going to take the branch or not, because if the condition is true, we're going to take the branch. If the condition is not true, we're not going to take the branch, okay? So we need the address, we need the outcome, and we also need to know whether this is a branch or not. So this is the 3W questions. So let's go and actually answer each of these three questions, because answering to these three questions can help us to kind of know how many cycles do I need to stall, what should I change in my processor pipeline, and so on and so forth to kind of fix this, okay? So when do I know that this is a branch instruction? Anybody wants to answer this? Yeah.
After the control.
After the control, right? So during the decode stage, I'm going to know that this is a branch because I basically just check the opcode. And if the opcode is one of those opcodes for the branch, I immediately know that this is a branch instruction, okay? So essentially it happens during this stage, okay? So I know it in the second cycle of the 5 cycle of an instruction that this is a branch instruction, okay? I know exactly which branch it is. Is it a branch equal or less than or greater than, whatever, right? So the second question, when do I know that where this branch is going to? Any suggestions? the where questions. In our pipeline stage design, does anybody remember that where we're going to know the address? Yeah.
Either end of execution stage or maybe never.
Yeah, so the answer is either end of execution stage or beginning of the mem, right? So if you remember, basically we need to know what is PC plus offset, right? So this is what you need to know in order to find the ver part, right? And if you remember, this was the part that we kind of like had this kind of register here, right? So we left shift from the immediate, we added with the PC, and this is where we're going to have the PC plus offset. So this is the end of the execution stage, or in other words, beginning of the mem stage, okay? So I know this when I have the immediate sign extended and added to my PC. That's when I have the address that I'm going to jump to, okay? So this is the where. And finally, whether we are branching or not, any suggestions when we're gonna know that? Someone else? Yeah. After the execution stage. So basically, again, in this whether to branch or not, this is actually when we're going to know it at this point here, right? So remember, we had a branch that was ANDed to the outcome of the 0, right? And this is, so basically this is my 0, and this is the branch. And if you remember when I was talking about where do we put that AND gate, I told you that I want to put that in the memory stage. The reason for that is this stage is already very kind of like busy, so I want to kind of make these stages equal length. So in other words, I'm kind of figuring out this in the middle of my memory stage, okay? This, the outcome of this that is equal to 1 is kind of known as kind of somewhere in the middle of the memory stage, okay? So to kind of like, oops. So to kind of like, you know, answer this 3W questions, the when part is known as kind of middle to end of the decode stage. The where part is, we can either say that it's at the end of the execution stage or the beginning of the memory stage. And the whether part is at the end of the memory stage, okay? Because we put that AND gate in the memory stage, so I know that this is going to be a branch at the end of the memory stage. Again, to kind of like, this is kind of where we're going to know whether this branch is going to take in or not, right? Any questions from these three? Yeah.
Why is the where and for secret? Like, why is it end of execution or beginning of
Why is it that?
Yeah, why is it or not just one of these?
Oh, so the question is why it's or end of this or beginning of that. It basically, so I mean, if I want to have it at the soonest, is end of execution stage. But end of execution stage is equally in terms of timelines at the beginning of the next stage, in other words, right? So I can, with forwarding, we can always like forward things from end of something to the beginning of the other. So end of one stage or beginning of the immediate next stage is the same thing for us. Yeah.
Why does when happen at the end of ID stage?
Why does when happens at the end of ID stage? Because when is that when we know that this is a branch instruction. And the knowing that whether this is a branch instruction happens in the control, which is during the decode stage. Yeah.
We make the decision of whether at the end of the memory stage, aren't we wasting a clock cycle?
So the question is, it seems that I'm kind of wasting by kind of doing this because, yeah. Yeah, so it's like if I had this here, then I could probably start things at the beginning of mem stage. But what I'm showing now is I can do things at the beginning of BrightMax. This is a good thinking, and this is what we're going to do. In fact, we're actually going to move things very, very early on. All right. So based on these, so now the question is, what will happen to my branch? Okay. So think about like something like this, that I have a branch instruction and I have a bunch of other instructions. Okay. And now the question is, if the branch is taken, then I have to skip all of these instructions and jump somewhere else into the memory. If the branch is not taken, then I have to basically continue these instructions, right? So this is the difference between branch taken and not taken, okay? So based on the 3W questions that I answer you, let's see what is happening. So the branch comes into the fetch state, then it goes to the memory, to the decode stage, and this is when we know that this is a branch. But can we actually fetch this new instruction or not? Since I don't know still whether all the three answers, I cannot like fetch a new instruction, right? So I cannot fetch this, so this is basically has to stay here. I cannot fetch an instruction yet here, so this is again has to stay here. This is the point that I'm going to know the kind of the direction of the branch, whether it's going to be taken or not. And finally, at this point, I'm going to know whether this branch is going to be taken or not taken, right? So at this point, it's really, if I kind of can forward the PC from here to here, this is the point that I kind of like can actually fetch a new instruction, whether it's taken or not taken, right? So I kind of like need to stop for stall the process over 2 cycles here. This is the same story of the kind of like pushing the bubbles and stalling and all those things until I know that this is indeed, for example, a taken branch, and I can kind of use the PC to kind of read a new instruction, okay? That's kind of like what I'm going to do, okay? So looking at this, that's, you know, for each instruction, I need to stall for 3 cycles. Yeah, I have a question.
Does this stalling and stuff affect branch prediction?
So the question is, does stalling in fact branch prediction? So far we don't do any prediction, okay? So we just don't know, we don't know the outcome of the branch, and we just want to stall until we know. We don't do anything fancy. But later on, we're gonna start, you know, adding these features to our processors. All right, so if you actually think about programs, interestingly, about 20% of your instructions in any program that you write are actually some form of branches. If you actually think about the way that you write code, there are lots of if and else's you use, lots of for loops that you use, lots of while loops that you use. All of them are essentially some form of branches, okay? So we are kind of like, and actually this is kind of like an average among different benchmarks. And we saw that, you know, 20% of all the instructions that we use are actually some form of control flow instructions. So if 20% of the time I'm stalling my processor by 3 cycles, you can go and kind of figure out how much time you're actually wasting in terms of number of cycles, right? So of course, the natural question is, can we do better? And by can we do better, the first thing that we can do is, can we actually make this number of stalls to maybe 2 cycles or 1 cycles or ultimately 0 cycles? That's what we're going we're trying to achieve, okay? So let's see how. So the first thing that we're going to do is this idea of what we call guessing or speculation, okay? So what we are saying is that let's do this trick that instead of waiting the processor to whether jumping or not jumping and then make a decision, let's do this kind of like trick that we pick, let's say for now, just a random pick that, you know, the branch is not going to be taken, okay? So we pick not taken all the times, and we're gonna continue fetching instructions, okay? So what will happen if we do that? So first of all, this kind of approach is kind of what we call guessing or speculation. And you're going to see this speculation approach a lot in this course as we move forward in the rest of the topics that we're going to talk about. And this could be either by the compiler or it could be based on the processor. Either one can make this guess. And as I said, this we call this speculation. So for now, let's say that we go with the not taken approach. So we any time that we see a branch, we're going to say that, okay, we're going to predict that it's going to be not taken. Okay, let's see how this helps us, and let's see what issues it bring and how we can fix that. Okay, so first of all, predicting not taken, what will happen to our pipeline and instructions? So same kind of examples that I showed you last time. Let's say I have a branch equal and I have I1, I2, I3, and I4. So once I do this, if the branch is really not taken, so what will happen is that the branch comes here, and then the next cycle, the branch kind of goes here. And remember the last time I told you, since I don't know the outcome of the branch, I cannot really fetch this instruction. But now I'm telling you that the moment that I see branch, since I know that the branch is actually kind of resolved at the end of this, I can basically fetch a next instruction, okay? So I'm going to fetch I1. I don't care whether this branch is taken or not. The branch goes here, and then I1 goes here, and I2 goes here, and so on and so forth, okay? So all of them kind of continues. So nothing really happening, right? So I'm just continuing business as usual. And the good thing about this is that if this branch indeed is not taken, then I'm not stalling at all, right? So the number of stalls that I have is exactly 0. So that's great because for all the not taken branches, I'm not paying any penalty, right? So the performance is as it was before without any changes to the system. And if you kind of like do some statistics analysis, we're going to see that it's actually not that bad of a decision. So if I told you that 20% of instructions in our mix are control flow instructions, some form of branches. Out of that 20%, there are either forward branches or backward branches, right? So either your branch kind of jumps back to somewhere else in the program or jumps forward in some part of the program, okay? So people have found that out of all the branches that we have seen on average, 50% of the branches that are forward are always taken, okay? More interestingly, the backward branches, 90% of backward branches are taken, okay? So in other words, if you think about this and then kind of do the averaging, we'll see that about 30% of instructions, of branch instructions are not taken branch instructions, okay? And if you kind of like, look back into the sequence of instructions, there are 80% of instructions that are not taken at all because they're not even branches. There are loads and adds and add-ons and so on. So these are basically things that are kind of do PC+4, PC+4. Out of this, the rest of the 20%, about 30% of this is also not taken. So if you kind of combine this, we'll see that around 86% of instructions are actually not taken instructions. That is, we just do PC+4, 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 okay? So 86% of the time in my execution of my programs, I'm actually doing fine because I don't need to be worried about controls and so on. There's only that 14% that I need to be worried about, and we're going to discuss how to fix that, okay? And again, if the math doesn't make sense, so first of all, these are just stats, so people have just like looked into large programs and they found these numbers, okay? And then how we actually move from here to here is just you have to kind of combine these this 50 and taken and 90 and taken, and you will get that 30%, trust me. And then this 80 plus 30, how it becomes 60 is just this 30 times 20, and that's how you get this 60, basically. 20%, 30% of 20% is basically 6% of your entire program. That's how it gets this 6%, okay? So 86% of the time, things are great because I don't need to stall at all, and I can just continue doing whatever I'm doing, okay? There's that 14% that I need to do something about, okay? And then, of course, the biggest question that we might have so far is what will happen if the branch is actually taken? And again, this is a correctness issue because if I just predict not taken and then just, continue executing instruction, those instructions are going to kind of update the register file. It might update your memory. And if you decided that, oh, by the way, this should have been not taken, I made a mistake, then it's already too late because your registers has been kind of messed up, your memory has been messed up, and so on and so forth. So we need a kind of a method for not making those big mistakes as well. So we want to keep not taking because that works 86% of the time, but I also need a mechanism to kind of fix what I messed up during those taken predictions, okay? So we call this process of kind of fixing things that we messed up flushing, okay? So essentially we are saying that, okay, we're going to this guessing or a speculation game that whenever we see a branch we're gonna guess that it's going to be not taken, and we're gonna continue, and I showed you 86% of the time it's okay, but very rarely they're going to be actual taken branch. In that case, we're gonna let things continue, but we're gonna have a mechanism which we call flushing. That's whatever those few instructions in between does, we're gonna flush that and we kind of recover our processor from those states, okay? So let's see how we actually do this. So this is basically kind of the idea that we're going to do by adding kind of bubbles for the flush, okay? So essentially the idea is that whenever we decide that we made an incorrect decision, so for example, going back here, so I have a branch, and so let's say fetch, decode, execute, memory, write back. I have branch here, then the branch goes here, then the branch goes here, and the branch goes here, right? So what will happen here is that at the end of this stage, I know that this is a branch that should be taken. Now I made a mistake. So what did I do is branch here. So at this point, I have, for example, I1 here, I2 here, and I3 here, right? This is a kind of current state of my pipeline. So what I need to do is that I realized that this branch was taken. So I incorrectly fetched this, I incorrectly fetched this, and I incorrectly fetched this, right? So I need to flush them out of my pipeline. So what will I do? Is that in the next cycle where this branch is going to this write back, instead of kind of moving this into the mem stage, I'm going to replace this with the same trick that I had before. I'm going to replace a bubble here, okay? I'm going to replace this with the bubble here. I'm going to replace this with the bubble, so replace this with the bubble. And here I'm going to fetch a correct instruction, whatever it is. I'm going to call it IM or whatever. This is basically the correct place that I should have fetched the instruction, okay? So I fetched 3 wrong instructions. They are in the fetch, decode, and execute stage. Still, nothing bad happens in terms of writing because I'm just doing some temporary values. But the moment that it's going to be shifted to the memory, that's when it potentially might write into my main memory. I'm going to replace that with a bubble, okay? So I need to replace 3 things with 3 new bubbles, okay? So that's kind of basically what I'm doing here. And again, remember the way that we were inserting bubbles? The way that we were inserting bubble was this mux that we kind of replacing the control with zeros, okay? So since I now need to replace the fetch, decode, and execute, now I'm going to need to add a few more bubbles here and here. So basically, same trick, and this time I'm replacing the few next instructions. So I'm pushing 3 bubbles into my pipeline the moment that I realize I need to flush. How do I know that I need to flush? Same hazard detection unit can help me with detecting the flush. So there will be 3 new kind of control signals, the instruction decode flush, execution flush, and then basically the same thing for memory as well. So I'm going to flush this, this, and this. So the 3 instructions will be flushed. Basically will be replaced by a control signal that is all 0. Question?
When you pass the bubbles in, will that also like clear out the forwarding unit if there's any register in there?
Clear the forward. So the question is, when you're pushing the bubbles, do you also need to do something with the forwarding? You don't, because forwarding again is the data, okay? So you might forward something incorrectly, but again, if you're pushing the control signal all zeros, nothing bad will happen because your register file won't be updated, your memory won't be updated, and your PC won't be updated. So you're basically forwarding some garbage with some garbage. You might add like 2 random numbers together. You might do all these kind of crazy things, but in reality, nothing happens permanently because permanent things are my PC, my memory, and my register file. All 3 are controlled by my control signals. All of them are zeros, so I'm good to go. Yeah.
The question, like based on the stats, so you're actually taking out of the control, so you're taking the branch off, not. So would it be more? take the branch, or could that make the, make the,
That's a great observation. So the question is, if you actually look into these numbers, it means that I'm kind of like, tricking you guys, because it seems that most of the time the branch is taken. So it might have more sense that if we did always taken, okay? The problem with the always taken is I need the address as well, okay? Because not taken is very easy. Not taken means that just do whatever you were doing, just PC plus 4, PC plus 4. You don't need the address of the branch, okay? So not taken is much, much simpler to implement than the taken one, okay? But that's why we are doing the not taken. Further, in future, you will see that we're actually going to say that, okay, oh, if I really, really want to do taken, what can I do? And we're going to actually add that to our processor as well.
So the difficulty is remembering the pieces for add and one branch that is doing automatic branch, then you would kind of.
So the question is, the difficulty is figuring out finding out the PC address of the branch that is going to jump to, right? And remember, that was PC plus offset, and that PC plus offset may not be known during the decode stage. It's only known during the execution stage. And remember, I want to just continue fetching. So I ideally want to know what should I do during the decode stage, and I don't have that number, right? But again, I'm going to actually show you how we're going to predict taken as well. So don't worry.
So if we keep proceeding as, like, the branch is not taken, at what point do we start the process?
So the question is that if we keep doing the not taken, at what points do we do the flush process? If you remember, I told you 3 W's, right? We know decode happens like the whether it's a branch or not, the direction is, the address is known at the execution stage, and direction is known at the memory stage. So at the end of the memory stage, we have all 3. So at the memory stage is when we're going to detect that this is a problematic one. So that's why we flush 3 things at that time. This is kind of like, as you can see in my example, during the mem stage, I see that, I made a mistake. This was the taken branch. So I already have this. Once this branch instruction is moving to the write back, I'm not bringing I1, I2, I3 with me. I'm replacing I1, I2, I3 with bubble instructions.
Is the flush signal generated by the control, or is it?
The question is that where does flush signals are generated? If you actually look into this, you will see that basically these are created by let's see. So these are, as you can see, is created by this control signal, right? Because why? Because we want to know that this is a branch instruction, right? And how do we know that this is a branch instruction? We check the opcode, we find that this is a branch instruction, so we kind of like do this. But there is also other things that I need to add this. Let me see if I have. Later on, I'll show you the full data path with everything, and you'll see that how this basically controller make a decision. Yeah.
On the right side of the slide, it says need to flush FE and DE. Does that just be fetch and reload?
This is the old thing. So you are talking about these, right?
Yeah.
So the question is, what are these? These are the same old thing that we had for load use data hazard. So this is on top of all those things that we had for data hazard. So remember, you still need to fix the data hazard. So you need to do the flushing for IF and ID and all those things.
No, I meant like specifically on the side of FE and DE. I can see the abbreviation. There's the notes on the right side. Not used right there.
Oh, this one?
Yeah.
Oh, yeah. So this is F and D. So fetch and decode. Yeah. Okay. So I'm kind of putting a note here that's kind of describing how do we do the flush. So as you can see, essentially all you need to do is knowing that your branch is going to be taken. So the moment that 0 becomes 1, you know that your branch is taken. So you connect that into your controller, and then your controller issues the flush, right? So this is kind of like, as I said, I'm going to show you the full picture, but this is the idea. Like the moment that 0 is 1, this means that your branch is going to be taken. And that's when you know that you made a mistake, so you have to go back and fix it, okay? So it's kind of like, just again showing I already showed you this. So this is branch, then branch goes here, then goes here, goes here. I1 comes here, I1 goes here, I1 goes here, I2 comes, and then 2, and then I3 comes. And this is the point that we realized that we made a mistake. So we need to flush these and then fetch the correct instruction. So at this cycle here, the branch goes here. The I1 doesn't continue coming. So here we're going to get the bubble. I'm going to show it with you. And then again, here I'm going to have a bubble. So this is a branch, this is a bubble. And then I'm going to put another bubble. And here I'm going to actually fetch the correct instruction. As I said, I'm showing it with IM or something. Okay. So 3 bubbles, a correct instruction in the fetch, and the branch instruction in the write back. That's what we're going to have. So here is finished. The bubbles are kind of continue here, and then IM comes here, and then at next cycle, IM plus 1 comes, and so on and so forth, right? So this things kind of continue as usual. All right. So what is the miss penalty in this case? So what is miss penalty? So miss penalty is basically if you make a wrong decision, okay, we have to flush 3 instructions, okay? So in other words, we need to stall the process. It's the same as if we had stalled the processor for 3 cycles, right? Because we're not really doing anything useful during that 3 cycles, and then we have to kind of flush them. So the only difference is that originally we had to stall the processor, now we kind of let them go and then we flush them, okay? So if you think about, for example, if the 70% of the instructions are taken and 30% of instructions are not taken, you can actually calculate, for example, what would be our miss penalty for a case that we have like 86% of instructions taken, and then we have 14% instruction not taken, okay? So if you look into the CPI of this, the CPI of this is basically 1. The CPI of this is equal to 3, right? Because we are kind of wasting 3 cycles for this to finish. And then if you kind of do the averaging, you will see that the overall CPI would be like 86 times, like the weighted average of these plus the weighted average of these, right? So 86% 1 plus 14% 3, and then you do the math, okay? Again, you can do it in Campus Wire for everybody and get some points. But essentially the idea here is that in most cases, I'm getting benefit by just not doing anything, and I get the CPI equal to 1. In 14% that I make a mistake, I basically needs to get rid of 3 instructions. In other words, I'm stalling the processor for 3 cycles, and that's where I'm going to get some what we call miss penalty, some performance miss, right? So that's the problem they're going to have with miss penalties. Okay. Any questions? Right.
If you miss, then when your CPI is 4, not 3, because it's, for example, if you stall for 1, then your CPI is 2. So when your CPI be 4 and you stall for 3.
Would the CPI be 4 if you stall for 3? Actually, yes. So it would be 4, and then this would be 4. Yes, it would take 4 cycles to finish. Yeah. Yeah. This one? Third one, I'm just doing the weighted average. I'm basically saying that if 80% takes 1 cycle and 40% takes 4 cycles, what would be the average CPI? So I'm, oh, this says weighted average. Like, just let me I'm just doing 86 times 1 and 14 times 4. 14 times 4. I'm just doing the weighted out. Okay. So this is the miss penalty I'm going to get. So far, what we are doing is we are paying 0 penalty 86% of the time. We are paying 3 cycle penalty 14% of the time. Okay. And this will result in some form of average CPI, which is much closer to 1 than 3, right? So most of the time I'm closer to 1. So it's 1 something, right? So now the question is, can we do better than this? Okay. So what can we do better? That's the question. Okay. There are things that I can do in order to make things better. The first thing I can do is reducing the miss penalty, right? So far we're seeing that it takes for us 3 cycles to figure out whether the branch is taken or not. If I can make this like 1 cycle or 2 cycles, then the miss penalty will be reducing, right? So this formula that I'm using here, essentially what will happen is that this part won't change, but this part, if it's like 3 or 2 or 1, then of course my CPI will decrease, right? So the CPI decreases, the CPU time decreases, right? So there is benefit of reducing this this number of stalls from 3 cycles to hopefully either 0 cycles or 1 cycles. Okay, so that's one thing I can do. So let's focus on this. That can I, and in order to achieve this, I essentially need to kind of resolve the branch sooner. If I sooner know that I made a mistake, then I wasted less number of instructions. So for example, had I known that the branch was taken during the execution stage or the decode stage, then I could, for example, flush only 2 instructions or flush only 1 instruction, right? So that's kind of the idea that we are going after. So how soon can we actually do this? Okay, and can we do it in execute, in decode, or in fetch? How many of you think we can actually do it in fetch? How many of you think that we can actually do it in decode? There are a few, and then the rest of you think that we can do it in execution stage, probably. Okay, so let's actually see how soon can we do it. We can actually do it in the decode stage. We cannot do it in the fetch stage because in fetch stage, we still don't even know that this is a branch, okay? If we don't know that this is a branch, how can we actually predict that this is taken or not taken? So the best thing that we can do is that during the decode, we know that this is branch, okay? If somehow I can manage to know that whether this is a taken branch or not taken branch during the decode, I basically can, just waste 1 cycle and then immediately fetch the correct instruction in the next cycle, okay? So see how can I do this? So let's see what we have in the decode so far. In the decode, we have the when one, right? We know already that this is a branch instruction, because our controller can check the opcode and we know that this is a branch instruction. So this is good, but there are 2 problems that we need to solve. One is the where and the other one is the whether. So basically, where this branch is this branch going to be taken or not? And if it's going to be taken, where it's going to be, right? If I can fix these 2 issues, then I can resolve the branch much sooner, okay? So let's talk about the where part, okay? So the offset actually, if you think about it, is already available in the decode stage, right? Because the offset is part of the immediate, which is part of the instruction. And all you need to do is basically doing the sign extension of your offset, and boom, you're going to have your decode stage. So all you need to do really is if I move the next PC calculation, that's kind of PC plus offset. If I put this into my decode stage, then I will have the address. The only problem is that I need to somehow add PC plus offset. And if I use some adder there, which I'm already using, then I'm set with the offset part. Okay. So now the question becomes for the whether parts, that whether, for example, if let's say, for example, let's focus on branch equal. So for a branch equal, I need to check and compare whether RS1 value is equal to RS2 value. How do we do that? We use the actual ALU. So we read the register file and we kind of compare these two within the ALU, and we have this special flag called zero flag, that kind of tell us whether this branch is taken or not. Okay. So if I can somehow move this comparison into the decode stage, then I'm going to have the answer of whether. And keep in mind that I already have the value of RS1 and RS2 during the decode stage. Why? Because reading from register file happens during the decode stage, right? So I already know the value of RS1. I already know the value of RS2. So I need to just do the comparison. And that comparison in regular design happens during the execution stage. But what I'm proposing now is that if I can add a comparator that kind of compare RS1 and RS2 during the decode stage, now I also have the answer to whether during the decode stage. Okay. So these things together, these things together will bring us to this design here. Okay. So notice these two kind of red ovals that I'm adding to the system. So basically I'm adding this thing here. And as you can see, this is basically, I'm moving the immediate generator to this decode stage. I'm putting the shift left and the adder here as well. So actually during the decode stage, I already know PC plus offset. Okay, so I'm good to go. And then the second thing that I'm adding is this block that is kind of like, get RS1 and RS2 and then do some kind of comparison. The block that I'm showing here is this kind of like, equal. But if, for example, we want to support less than and greater than and other sort of branches, essentially I can just add all of these things here. So what is really changing is that previously I had to kind of move this here, and I had this zero block here, and I kind of move everything back. Now I'm telling you that basically you can compare this, and then you can tell your controller, can basically connect the signal out of this to the controller, which I'm not showing here, but basically that's what we're going to do. Okay. So now at the end of the decode stage, I know that this is a branch. The controller tells me the opcode. Now I have also the PC plus offset at this point, again happening during the decode stage. So this is PC plus offset. And now I also know that whether RS1 and RS2 are equal to each other, again, there will be a signal coming out of this that I can use in order to decide whether this is a taken branch or a not taken branch. Okay, so all these three helps me to resolve the branch by the end of the decode stage. Okay, yeah.
Yes, no question. So now that we're no longer doing that computation in the execute stage, I'm not too clear, what happens when we get a zero of that ALU?
I'm just getting rid of the zero. So the question is, what happens to the zero? I'm just getting rid of the zero. I no longer need it, right? So the cost that I'm paying is that I'm kind of adding a mini ALU in the decode stage. I'm getting rid of the zero completely. Yeah.
Will we be making trade-offs in terms of the cost? Modification like this will at this stage take longer to settle.
So the question is, if I'm adding all these things, then it seems that, I'm kind of making my decode stages a little bit longer. It does, but generally, as long as this is not longer than these two, then I'm kind of, so there are trade-offs that's happening for this, but this is kind of like, if you design this very fast, and this part is kind of happening with the register read, so this part is not really a big problem. The slowest part is this part, because you need to read the register file and then do the comparison. But the comparison is like a very simple logic design, so it's not significantly adding to your design. You still, this data memory is really the slowest among these. Yeah. That's a great question. So you might actually run into some form of data hazards, and I'm going to actually explain what that is and how we can fix it. Any other questions? All right. So so we are resolving the data and decode stage. One thing that as I said, so this 0 is not shown anymore. There will be one control signal from here to here. I'm not showing it here, but just keep in mind that there is a blue signal that's kind of coming out of this controller. Let me actually kind of like coming from here and goes here. Okay. Since we become very messy, we didn't show it here, but there is a control signal here. Okay, same 0 signal basically. All right. So now with this, what we really need to do is, if I know that my instruction is resolved in the code, so going back to the examples that I gave you, so let's actually kind of revisit that example. So I had branch, I had I1, I2, and so on and so forth, right? So if I do fetch, decode, execution, memory, write back, now I have branch here. Next cycle, the branch goes here, and I1 comes here, right? So now at the end of this cycle, I know that, the branch has been resolved, right? And the branch is taken. So what I would do at this point is, now the branch goes into the execution stage, and now I know that I made a mistake. I predicted not taken, but this branch is taken. So what I need to do is, now I need to flush this I1. So this I1 goes to the decode. Instead of I1, we put a bubble, right? And let me kind of like make this a little bit nicer. And then I put the branch here. Okay, so the bubble here. And now I can basically fetch that IM thing that was kind of way over here. That's the correct branch that was kind of jumping here. Okay, so I put the bubble here, the instruction here, and the branch here, and this thing continues, right? So basically IM comes here, bubble comes here, branch comes here, and then maybe IM plus 1 comes here, and so on and so forth. So I basically reduced the number of stalls and number of flushes from 3 to just only 1. Okay, so make my processor significantly faster. I couldn't do it 0 because if I wanted to do 0, I had to resolve it at the fetch state, and we couldn't do that, unfortunately. But at least I can do it at the decode stage, which means that I only pay 1 cycle of miss penalty. Okay, so that's kind of the idea. So how do we do that? Basically, if you go back here, we still need to flush. Excuse me. We still need to flush things. So we still need to kind of push a bubble and stuff like that. So what we're going to do is that we're going to kind of like push this 0 here, and we kind of push a bubble from fetch to decode if we see that we made a mistake. Okay, so if that 0 signal tells you that, oh, okay, this branch was taken, what we are going to do is that we're going to push, instead of I1, we're going to push a bubble into this instruction. Okay, so this is where this kind of IF flush and this kind of signal that goes into the pipeline is means. So this is your 0, this is your flushing the pipeline. Okay, yeah.
So when we take the branch instruction, during the code stage, will the branch instruction then still go on and even though you know?
Yes. So the question is, when we are detecting basically this is a branch, the branch basically continues in this stage and this stage, right? But again, branch doesn't do anything in any of those stages either. In previous case, we had to do the branch of kind of doing a 0. So we still do the subtract, but there is no 0 signal anymore. So we just do an arbitrary subtract here. There's nothing going on in the memory stage and nothing going on the write back stage. So you're basically just moving the branch to the later stages without really doing anything else.
Yeah, the flushing between the later stages.
The question is, do we need the flushes for the later stages like these?
Yeah.
You need it for some other things. But technically for this, you no longer need it. Yeah. For the branch, you don't need it. But we keep it because kind of for completeness. But there are other scenarios that we're going to have it. I'm going to describe later. Yeah.
So the branching signal is still the branch of the control and the end of it.
Say it again.
Like the new branching signal is still like the signal from the equal and the.
Yes, so this is going to be your zero signal or your branch signal that goes into the controller and then controller issue the flush. Any other questions? All right. So I kind of show you this already. So there's going to be a data hazard for this because I'm going to read these two values, but I'm going to update these values here. I'm going to pause here. I'm going to describe that data hazard later, next time that we're going to talk about this. Just keep in mind that this is kind of end of what we're going to cover in quiz 1, except this few slides that I'm going to cover the beginning of next class. Okay, so end of this lecture 7 is basically your quiz 1.
Now time for question.
Yeah, give me a second.
Okay.